Welcome back to Calculus 2. This is part 2 of our lecture on area between curves. In part 1 was some basic introductory examples, as well as deriving the formulas in 2 different ways. Now in part 2, we'll be looking at some of the more complex topics related to area between curves. All right, one of the ways we can kind of take a look at something a little more complicated, still dealing with the concept of area between curves, is one possibility here. Perhaps the graphs of the two functions intersect several times over the region A to B. Now, we already saw within an example in the first part, if the curves intersect, we can find the intersection points. Well, what we kind of have to do here is split the entire region into 3 separate ones here, like for example in this sketch. Now maybe the curves intersect only once. Here the curves intersect twice in our sketch. Could be any finite number of intersection points within an interval. We would split up that larger region between those curves into smaller ones. And then on each of those smaller regions, we apply our concept. The area of that region should be the integral of the upper function minus the lower function. So for this general sketch here, where there are 2 intersection points within the interval here, the total interval is A to D. There's 2 intersection points labeled B and C, and that gives us 3 separate regions. Now, I want to point out and make sure you understand that due to the curves intersecting, they kind of switch and crisscross, reversing the role of which one might be the upper and which one might be the lower function. So just be cautious of that. There is a way to define this as a single formula using absolute value, but it's rather tedious since absolute values aren't very easy to integrate. So here we can split this up to 3 separate regions and then sum all 3 of those areas. A1, that first region, we integrate f of x minus g of x, since it is f of x that's on the top. And then for A2, we integrate g of x minus f of x, since g of x for the region A2 is the upper function. So again, due to that kind of intersection, the upper and lower function, the role of f and g switch on the different intervals. All right, now that is one way the problems can become a little more complex. Maybe a region has to be split into a finite number of simpler regions. Another way that we could have a more complex region is, suppose for this sketch, maybe there is a single lower function, but the region is bounded above by 2 different curves, y equals f of x, and sketched here y equals h of x, that maybe intersect somewhere in the interval. Now this is a little bit harder since we can't apply our basic formula, upper function minus lower function, since there's 2 different upper functions here. Well, kind of like we were mentioning above about breaking a complex region into a smaller number of simpler regions, we can do the same thing here at that intersection point where f of x and g of x, or sorry, h of x, where their graphs intersect, that occurs at what we labeled here, x equals c. We can basically split that with a vertical line right at x equals c into 2 regions on either side, A1 and A2. A1 is bounded above by f of x and below by g of x. A2 is bounded above by h of x and below by g of x. So here, if the upper function kind of is bounded by, or upper part is bounded by 2 different functions, we can split it to 2 separate regions. The integrals here would be one from a to c of f of x minus g of x. And then for A2, it'd be an integral from c to b of h of x minus g of x. All right, let's go ahead and apply these concepts with an example. We'll take a look at one example for each. And this one is probably the most complicated of all the examples throughout this lecture. So I'd like you to first make an attempt at it. It sounds rather simple. Find the area for the region bounded by the graphs, and you're given the equations, a quadratic function, some sort of parabola, and y equals 4x plus 16, some sort of line or linear function. And you're given the endpoints of the intervals, -2 to 5. Now, one way this might get a little bit complicated, maybe first see this without sketching the graph. See if you can determine if those two curves, y equals functions of x's, maybe if they intersect. That might tell you then, within the larger interval, -2 to 5, if you have to split it up, like we mentioned in that first way a region can become more complex. So maybe first, see if you can find intersection points between the quadratic and linear function, and then see if your sketch confirms that. We'll check in several minutes. Welcome back. Hopefully you kind of got through it. Let's first start with a sketch to give us some idea of what's going on. So here we have one. Hopefully the scale is viewable. I don't have the x and y axis to scale on the same kind of units. But you can see we have the parabolic graph there. That's the y equals 2x squared plus 10 on the bottom. And then what looks to be in black is the graph of the linear function, y equals 4x plus 16. Now you can see over that larger interval from -2 to 5, there are two intersection points. And it looks like, from the graph, those intersection points correspond to x equals -1 and then x equals 3. Now, an algebraic calculation should confirm that. If you set the quadratic function equal to the linear function and solve the equation 2x squared plus 10 equals 4x plus 16, you should be able to confirm that from your sketch here, that there are two intersection points. That quadratic equation, if you subtract all the terms to one side, it will factor, and from each factor you get a solution. So factorization gives you the solutions for x equals -1 and x equals 3. That's confirmed in our sketch. So what we determined is within the interval -2 to 5, that's the larger or total interval, there are two intersection points for the curves within that interval. So if we have two intersection points within an interval, we have to split the bigger region into 3 different parts. And you can see that again in your sketch with the 3 regions we labeled A1, A2, and A3. Now, if you got stuck maybe earlier, maybe with the visualization and then the intersection point solved for, maybe that'll be enough for you to complete the problem. So if you need to, pause the video again, make an attempt. We'll check in about a minute or two. All right, let's go ahead and finish this problem. So we're going to set up the integrals for each of those 3 regions. We're going to apply the idea, regions that are bounded by 2 curves, their area, we integrate the upper function minus the lower function. And just be careful when you're looking at each of those 3 regions that you're careful in selecting the correct upper function. There's some switching, reversing of the upper and lower functions between those 3 regions. All right, now this gets a little tedious, but basically once you kind of simplify after subtracting there within the integral, you can apply the power rule for antiderivatives since all the integrals involve just powers of x. It gets a little tedious to apply the fundamental theorem of calculus. Be careful with, for instance, A1, both of the endpoints are negative, so there's going to be a lot of possibility for sign errors. But if you go through that correctly, you should get A1 evaluates to 14 thirds, A2 evaluates to 64 thirds, and A3 evaluates also to 64 thirds. Again, that's probably tedious, actually maybe harder than some of the calculus since it's a kind of a tedious calculation with fractions, but it completes the question, giving us the total area for the region bounded by those curves, 142 thirds. Okay, so this is kind of how we would approach for a problem where the region has curves that intersect several times within the interval. Now let's take a look at maybe the second way a region can get more complex. If maybe for the region, we have a single lower bounding curve, but the region is bounded above by two different curves. So again, pause the video and make an attempt at this one. Give yourself several minutes. We'll check in after that. Okay, let's go through this. First, I want you to realize here we're given three curves. Y equals 0, you can think of that as the x-axis, but think of that as the equation of a horizontal line. So we have a region bounded by three curves, y equals x squared, y equals negative x plus 2, and y equals 0. It's likely then that either the upper part or lower part of that region has two different bounding curves. All right, if you were to sketch that here, the lower curve, y equals 0, is the x-axis. And if we sketch these two simple graphs, y equals x squared and y equals negative x plus 2, we get kind of a curvy parabolic shape on the left, and then that kind of line with negative slope on the right side there. All right, so for that region, the bottom curve or lower curve remains the same, but the bounding part above is bounded by two different functions. Those two functions, y equals x squared and y equals negative x plus 2, they intersect. Hopefully you found those intersection points. Simple quadratic equation. You should find that those points of intersection come out to be -2 and 1. Since we're looking at a region here, kind of the bounding region occurred in the first quadrant, we can forget about x equals -2. And then we just consider x equals 1. All right, so from our sketch, we're going to kind of integrate that region over the interval of x values from 0 to 1. And since we have two different upper functions, we'll split this larger region into two simpler regions. The region A1 is just going to be the region from 0 to 1. The upper function is x squared, and the lower function is just 0. So we basically just apply the fundamental idea, definite integrals represent area beneath a curve, provided they don't go below the x-axis, and we apply that here. No harm in applying our new area formula, upper function minus lower function, since the lower function is 0. You can add or subtract 0 with no problem. So the integral is rather simple. The integral from 0 to 1 of just x squared, and that should evaluate to 1/3. The definite integral representing the area for A2, the region between the graph of negative x plus 2 and y equals 0, is also a simple integral. It's an integral from 1, the intersection point, to 2. And it's a simple linear function. We just integrate that using the power rule. You should find that evaluates to 1/2. All right, if you add those two areas together, 1/3 plus 1/2, it is not 2/5. Be careful, use a common denominator. You should get that comes out to 5/6. Okay, so really, hopefully not that bad. Example 2 was probably more complicated than this, but this is also a good example to motivate an alternate approach. So far, we've been looking at setting up everything as integrals with respect to x, where our functions y were functions of x. Well, we can kind of flip things around and do this for areas for certain regions where it's a little more easier to define them as x as a function of y. So let's take a look at how that works. This is really not a new formula, but just a different version. So the first way that we introduced this was where we had the curves y as functions of x. We ended up with the kind of end result that the area is the upper function minus the lower function. So we wrote that as the integral of y upper minus y lower, where we interpret y as some function of x. All right, now this is an easy way to evaluate regions where you kind of have straight sides. In other words, x equals a and x equals b are equations for vertical lines, but it's the top and bottom curves, or top and bottom bounding curves, that are curvy. So here, we can think of that as an integral integrated with respect to x. We go from basically, you can kind of see in the sketch, the rectangles going from bottom curve to top curve. Now there is regions where maybe a little more complicated, since we're not really as comfortable usually sketching x as a function of y. That's a little unfamiliar. But there are regions where it is the top and bottom curves that are straight, now horizontal lines, but it's the sides, the left and rightmost bounding curves, that are no longer vertical lines or straight, but curvy. So we kind of change the orientation. We can do that by describing, instead of y as a function of x, x as a function of y. And instead of thinking of a region bounded above and below, it's a little more proper in this orientation to think of a region bounded by curves on the right and left. So we have two similar formulas. In integration with respect to x, we have it as y upper minus y lower, where y is a function of x. This new version, we have it here as an integration with respect to y, since we're interpreting x as a function of y. Both these formulas, we integrate with respect to the independent variable, or input variable. So this new formula, we can think of it as an integral from c to d, that's along the y-axis, but now of the rightmost function minus the leftmost bounding function. What changes here is the functions now are x as a function of y. Now, example 3, that is a good example. We can do that in several ways. We saw it in example 3 as we work through, splitting that region into two simpler regions and applying the integration with respect to x version, y upper minus y lower, twice. Well, example 3, we can do it a separate way. So let's revisit example 3 and see if you can complete this, but as that new version. Just to flip back to it in case you didn't copy it down, we're going to apply this new version down at the bottom there, an integration of the rightmost function minus the leftmost function, and we integrate that with respect to y. So let's see if you can use that and apply that here. We had in example 3, the final answer came out to 5/6. See if you can set that up and evaluate that from here. We'll check in a few minutes. All right, welcome back. Hopefully this was not too bad. Most of the work here is in taking the original functions given as y as a function of x and then solving them for x to express that functional relationship instead as x as a function of y. So solve each equation for x. The work should be minimal. Just be careful with the kind of the leftmost bounding function. y equals x squared, when you solve that for x, you do so by taking the square root. We should append the plus or minus in front, but since we are in the first quadrant, x and y are both positive, so we can, as usual, ignore the negative since we're in the first quadrant where x and y are both positive. All right, so we have our rightmost bounding function as x equals negative y plus 2, our leftmost bounding function, x equals square root of y, or y to the 1/2. Now the resulting integral is simple. The benefit of this approach to example 3, using the integration with respect to y version, is we only have to calculate a single integral. Example 3, as we first went through it, the concepts might have been simple or simpler here, but it required us to split the region into 2 different regions and evaluate 2 different integrals. So kind of here, what I'm advocating is to be lazy. You have to, of course, know this new formula, the integration with respect to y version, but if you know that and are comfortable with it, you can be lazy and evaluate 1 integral instead of 2. And if we apply the power rule here, the formula we're thinking of it as the rightmost function minus the leftmost function, the resulting integral should be pretty simple, just some basic calculations with fractions. Notice it's very nice to plug in x equals 1, or sorry, y equals 1 to this, and then y equals 0. Plugging in 1, you just get powers of 1 is 1. Plug in 0, everything evaluates to 0. So you should find here, you get the same total area as we found in example 3, 5, 6. All right, that pretty much does it for everything I wanted to cover for this lecture on area between curves. It's a kind of simple idea, but we're going to build off of this to introduce volumes, arc length, and surface area, other geometric quantities as we go throughout the course.